Lab 4, Modeling Spring Motion. Our objective in this lab is to model the motion of an oscillating spring and analyze the energy changes throughout that oscillation according to the energy principle. The procedure was to first observe real-world motion, and based on that observation, calculate our spring's stiffness, length, etc., and input that with forces to model the motion. We needed to confirm our model was accurate representation of the observed motion, and then used Python's graphing power to visualize energy changes. We've ultimately analyzed whether the energy principle accurately describes those energy changes. The result, of course, is that we find we are able to predict observed motion, though not perfectly, and that our model does satisfy the energy principle. We also additionally ask, how does the period of oscillation in the x direction vary from the period in the y direction, and why? The first step was to observe the motion of an object attached to a spring and to record data directly from that observation, including mass, spring length, the mass position throughout oscillation, and the period in the y and the x direction. Next, I used the observed period and mass to calculate the spring stiffness K, and then applying Newton's second law for the moment when the mass hung at rest at the end of the spring, I was able to set the force of gravity equal to the force of the spring, and again applying observational data, the length of the spring at static equilibrium, I was able to calculate L0, the relaxed length of the spring. With this information, I was able to set definitions in the program in Python for the length of the spring, the unit vector defining the direction of the spring, and S, the magnitude of the spring's stretch or compression. With all this prepared, it's now possible to write a while loop that calculates the forces acting on the mass, the force of gravity, and the force of the spring, and to use Newton's second law to predict the motion of the mass. It's then necessary to update the spring's position, calculate the new unit vector in the spring's direction, and the new spring stretch. It's important to note that we expect the while loop to be an accurate representation of the real motion because we've based it on Hooke's law, that the force of the spring is equal to the constant of the spring stiffness times the stretch of the spring in the direction of the spring. It is the job of the Python program to calculate this information for every 210th of a second, that is every delta t. With this information input, it's now time to watch the model and see whether it's an apparently good approximation of the observed motion. This does look to be at least similar to what we expected to find based on our observations. Confident that the model at least resembled the observed motion, I next imported the observed motion and overlaid it on the model. You can see here that the model is in fact a pretty good approximation of the motion we observed. To find out just how good an approximation, however, I had Python produce graphs for the x position and the y position in regard to time, and you can see that the y position is in fact very, very accurate, although there is some discrepancy in the x position. Having confirmed that the model is at least a pretty good approximation of the real observed motion, I next put in code to calculate the kinetic energy, gravitational potential energy, and spring potential energy throughout the oscillation period, as well as the changes in those energies. Utilizing these calculations, I had Python output a graph with the potential spring energy, potential gravitational energy, kinetic energy, and the sum of these three, the total energy. As we would expect, potential spring energy is positive and varies with the oscillation of motion. The potential gravitational energy is negative and varies with the oscillation of motion. The kinetic energy is near zero. We didn't expect the mass to have much, and the total energy is constant. Of course, the real power of having Python graph the energies is being able to graph the changes in energies. Here that shows us that as spring potential energy increases, gravitational potential energy decreases, and vice versa. And most importantly, it shows that the change in total energy is always zero, that the energy in the system does not change. This is the confirmation of the energy principle that we were hoping to find. So we conclude that our prediction based on Newton's second law is relatively accurate, particularly in the y direction, though it seems some factor is missing in regard to x direction prediction. And we also conclude that the energy principle is confirmed by the model of this motion. We were also asked to consider how the period in the x direction differs from the period in the y direction, and why. I calculated those periods and found their difference to be 0.132 seconds. If we had expected them to be the same, that's a variance of 8% of the period we had anticipated. But if we think of the swing in the x direction not as the swing of a spring, but of a pendulum, and we calculate the x period using length of the pendulum 0.7 meters, the length of the spring with the mass attached at static equilibrium, we then predict a period that is only 0.027 seconds different from the period we actually observed, a difference of only 1.6%. This accuracy suggests that we need to think of the motion in the x direction and the motion in the y direction as being due to fundamentally different forces, or different types of motions. One is the motion of a pendulum, and the other the motion of a spring.